Now let's talk about Charles' law. Charles' law is an example of a gas law that has a direct relationship between two properties. And in particular, volume is directly related to temperature. So it turns out when gases are heated, they spread out. This is going to help us explain how a hot air balloon actually works. Let's imagine here you have four molecules of gas, and we can define its volume by drawing this box around it. Now, if you heat up those molecules, the gas will be having more energy, and so as they move more energy, they will move farther away from each other. So if we were to define that volume, it is at a larger volume. See, that is the meaning of a direct relationship. When temperature increase, the volume also increase. So how does this explain how hot air balloons work? Can you tell me the density between this gas and this gas? Density is mass over volume. So in this case, when you have increased the volume and haven't increased the mass, the density then will decrease. So in hot air, it is less dense. And what do you know about less dense stuff? Right? Less dense will rise above, will float. When we talk about liquids, that is the case. When we talk about gases, that is also the case. So a less dense gas will float above the more dense gas. So hotter air will rise above cooler air. And that's how a hot air balloon will rise above, because it is hotter in the hot air balloon than it is on the outside air. This you can also apply in your home. If you live in a two-story home, you may notice that upstairs is always warmer than downstairs. That's because hot air is always going to rise and rise to the second floor. Or if you only have one floor, you can check this phenomenon by touching the air on the top of your room versus the air on the bottom. If you see there's a difference in temperature, you should see that in the top layer of your room, the air should be hotter, and on the floor, it should be cooler. All right, so let's take a closer look at Charles' law. Again, a relationship between volume and temperature. We're going to use our piston and our chamber once again. Okay, so we can measure that in the first state, it has a temperature of 200 Kelvin and a volume of 1 liter. Now, if we were to increase the flame, adding more heat into this sample, let's say double it from 200 to 400, what do you think will happen on a molecular level? When you increase the temperature, what happens to the molecule? They will bounce around much faster, right? Temperature is directly related to kinetic energy, right? Kinetic energy means it can move around faster. As it moves around faster, it will bounce against the wall at a higher rate also. Now, if it bounces against the wall at a higher rate, then its pressure will increase. But remember that in Charles' law, pressure must be constant. How would you counter that? How would you decrease the pressure? The only way to decrease that pressure to make it constant is to increase the volume. As the volume increases, the balls, even though it's moving faster, has a larger distance to travel. So it will hit the wall at a slower pace than it was at a small volume. So because of this, as temperature increases, volume also increases. So here we measure that the volume increases to 2 liters. Doing the same math approach, we can say this time though that, let's say, taking temperature divided by volume, what do we get? In this case, we get 200 Kelvin per liter. And in the second case, temperature of the second state divided by volume of the second state, we also get 200. Again, we see the same number appearing, so we call that a constant. As long as the number of molecules don't change, so we see that the number of molecules don't change, and the pressure don't change, then this is a true relationship. They are directly related to each other. So if we take T1 divided by V1, it will equal T2 divided by V2, and it will equal T3 divided by V3. It will equal to 4 divided by V4, or so on and so forth. So we can truncate that, simplify that, and just simply say that anytime you take a temperature of one state divided by the volume of one state, it will be equal to the temperature of the second state divided by the volume of that second state. That is called Charles' law. Since Charles' law is a mathematical relationship, we can manipulate like any math relationship. V1 over T1 is now equals to V2 over T2. It's just this equation flipped entirely. So either relationship you can consider as Charles' law. Example of Charles' law states a balloon has a volume of 785 milliliters at 21 degrees Celsius. If the temperature drops to 0 degrees Celsius, what is the new volume of the balloon at constant pressure and moles? Okay, so it says that we are at constant pressure and moles. That means I can apply Charles' law. If it doesn't say that, I cannot apply Charles' law. So let's write down what we know. We know that T1 initially is 21 degrees Celsius, and we know that T2 finally becomes 0 degrees Celsius. And we also know that V1 is 785 milliliters. And V2 is what we are looking for. Now, as I have mentioned in the previous section, when we are dealing with the gas laws, you have to use units of Kelvin for temperature, not Celsius or Fahrenheit. So if you're given Celsius, you have to first convert it to kelvins. Okay, so if I were to convert T1, 21 degrees to Kelvin, is 21 plus 273, which is 294 Kelvin. And T2 is 273 Kelvin. Alright, so again, let's say I'm solving for V2, right? So T1, since I'm solving for V2, I'm going to use the opposite equation of V1 over T1 is equal to V2 over T2. Okay, so the reason why I did this, because then if I want to solve for V2, I just multiply both sides by T2. Right, T2 will cancel out each other, giving me my equation. That V2 is equal to volume 1 times temperature 2 divided by temperature 1. So that plug those numbers in. Volume 1 is 785. Temperature 2 is 273, and temperature 1 is 294. Again, I should see that my kelvins will cancel out, giving, whoa, what happened? 285 is ml. I'm sorry about that. Leaving my units of milliliters, right? So on our calculator, what do we get?
785 times 273 divided by 294.
We get that V2 is 3 sig figs each. So that's 730 ml. Okay, again, let's double check if our answer makes sense. It was at 21 degrees and it decreased, and we know that that temperature and volume are directly proportional to each other. So our volume 2 should be smaller than volume 1. Is it smaller? 730 is indeed smaller than 785. Good. Okay, so let's now do a checkpoint using Charles' law. So the question reads, a balloon has a volume of 2.3 liters at a pressure of 755 millimeters mercury and 28 degrees Celsius. What will be the new volume in liters of the balloon if the temperature is changed to 36 degrees Celsius, assuming the pressure and moles do not change? Okay, so the pressure and moles don't change. So the information of the pressure being 755 is pretty irrelevant to us, right? So this is an application of Charles' law, so we only care about volume and temperature. Let's plug in the information that we do know. A balloon has a volume of 2.3 liters, so let's say that is its initial volume at 28 degrees Celsius. What will the new volume, so we don't know the volume of the balloon if the pressure is changed to, if the temperature is changed to 36 degrees. Alright, again, so Charles' law says we have to use Kelvin. we have to convert this to Kelvin, which is 28 plus 273, which is 301 Kelvin, whereas 36 plus 273 is 309 Kelvin. We want to solve for V2, so again I'm going to say that V1 over T1 is equal to V2 over T2. To get V2 by itself, I multiply both sides by T2. Therefore, cancels out. Okay, so V2 is equal to V1, 2.3 L's, times T2, 309K, divided by T1, 301K. And again, the K cancels out, giving us units of liters. That's always good to see.
2.3 times 309 divided by 301.
How many sig figs? 1, 2 sig figs. 2.4 liters. Answer is D. Again, make sure that it makes sense. You have temperature increasing, so volume should increase. It did, 2.3 to 2.4 liters.